Okay, yesterday we stopped at this concept. If we have a force, yesterday we talked about principle of transmissibility. So if you have a force and you want to transfer it from one end to another end, for example, the diagram on the top. So if you want to move the force on the right to a new position from A to B, you can do so as long as it's fall along the axis line. However, if you want to move a force with the perpendicular to the axis, right? If you move a perpendicular force along the axis, let's say you move A from position A to position B, the magnitude still maintain, the direction still maintain. However, it will generate a moment at location B. So these are the consequences or the results if you transfer from one location to another location. And if you transfer a force which is parallel to the axis, not parallel, along the axis, and perpendicular to the axis. Right? And we can transform the forces. We convert the forces that inside these complex systems. So if you see this diagram, you have force 1, force 2, F1, F2, and then there's a moment. You can summarize these systems in the moment form, where you transform F1 multiply by the R by using right hand rules, R cross F, you get one moment. F1 R1 cross F1, you get first moment. F2 cross R2 cross F2, you get M2, and combine with the given moment, you get the resultant moment. So yesterday we stopped at here. Okay, stop at here. So start from this chapter, you should be able to see system on the left will equal to system on the right. Okay, this one, the one that you see on the left, this one very high chances will be in the question. The one that you see on the right, this one will be the expected answer in your solution. Okay, so what you do is that when you see this kind of system, what you do, you focus on a point that is given in the question. For example, if the question give you a origin O, you focus all the force, the moment to the O. Okay, so you move your force. Okay, you move your force because the force is not aligned with the axis of O. So you draw X, Y, Z or three axes. You move your F1 to the O. It will generate moment. For example, this one. You move F to O. When you move F that is not on the axis, you move F1 to O. The F1 still remain, but it will generate moment by having R cross F. By having R cross F, because you extend this F1, you extend this F1, your right hand rules tell you R cross F, you will get an axis, the moment coming up from the screen. You get M1. Okay, this is principle of transmissibility. Means you can move your force from one location to a new location, but it will generate moment. Okay, so this one, you move to here, F1, but because of this motion, you generate a moment using your right hand rules. R cross F, because you extend the force. You can extend the force. The arrow will be here, so R cross F, get this moment. Then when you write moment, please write carefully the sub there. So you have M1 equal to R cross F. So write carefully also in your notation or in your diagram, R1 cross F1. Then you do the same for F2. You move F2 to O. You move F2 to O location. Same when you move F2 that is not parallel to the axis, you move perpendicular to here, you will generate F2 and also generate R cross F. R cross F, you're generating M2 over here. Okay, R cross F. R2, F2. Then the last one, moment on the object, you can move anywhere. This moment, you can move anywhere. It doesn't affect the moment. So these are the steps. So again, the one that you see over here, this one on the left will be the one you see in the question. This one is expected in your answer. You need to draw this diagram and equal to this diagram. Then from this middle diagram, you need to work back like what you learned in chapter 2, finding resultant. Okay, you have F1, F2, you need to find F1, F2 resultant. You have three moments, moment 1, moment 2, moment 3. You need to find resultant for moment. Okay, at the end, you arrive at this diagram. Okay, so again, the one on the left, you will see in the question. You need to convert this diagram on the left to the middle one. Okay, so how you transform the left diagram to the middle one? By using principle of transitability. So you move your force to one of the point, move everything to one point. In this case, we move everything to O. So when you move your force to somewhere else, something happened. So you combine all the result here. Once you have all the things on the single point, remember to recall what you learned in chapter 1, chapter 2, finding resultant for force and moment. So F1, F2, this direction, you'll find resultant. Okay. And MO1, MO2 combined with M, you get another moment, resultant with the angle. Okay. So notice that FR, the resultant force, is independent of the location of O, since it is a summation of forces. So this one, FR, is independence of point O because it is a sum of these two forces. However, this resultant, this MR resultant is depend upon this location. Why? Because if you move the OM to somewhere else, it will generate different moment. The moment MO1 here is depending on the R distance, R2 distance. Okay, this resultant is a combination of MO1, MO2, and M. If you shift this MRO to somewhere else, it will not get the same value because of R1 and R2. Okay. Resultant of force, you can shift anywhere. Doesn't matter because this is a vector direction. Magnitude still same, direction still same, direction still pointing up. Because you combine all the F1, F2 to get the resultant. Okay. So this is the meaning of this statement here. Okay. Okay, the rest you read, I already explained. Okay. Previous class, we also mentioned the word free vector. Free vector. So MRO is a free vector, can add any point on the body, although point O is generally chosen for the application. Okay, so we simplified the diagram on the left to a middle one. We call it equivalent or resultant, single resultant couple moment. We arrive at this equation, but you're already familiar with this formula. If you have many forces, you just get the resultant by combining all the force. You get resultant the moment by combining all the moment that you see on the bodies. Okay. Now, what is the difference between this section compared to the previous section? This section, we are moving the force around. The previous section is so simple that the force is given at exactly one location. Then you combine them. So this section, we start to transfer forces from one location to another location. And from here, you can break into X, Y, Z location. Means all the moment resultant, okay, or resultant will equal to the sum of moment at a certain place. F resultant will equal to all the force. So these two general equation you can break into X, Y, Z equation. Like what you see on the screen here. You can look in resultant in X direction, resultant in Y direction, moment in one location. So for example, the traffic light, when you hang the traffic light had a weight, weight 1, weight 2, and have a distance. It will generate stress to this point. So if you design not very well in connector here, you're going to hurt someone. Okay, you're going to hurt someone. So you can convert these two forces to a resultant at point O. So W1 multiplied by D1, you get first moment. W2 multiplied by D2, you get second moment. You combine moment 1, moment 2, you get resultant O at point O. Okay. And then, yeah. And then you have here, when you transfer these forces to this point, remember it generate moment when you move these two. When you move forces from one perpendicular distance, the forces still there. That's why you see there's a WR there. WR, because you combine the two forces, you move from one location to a new location, the forces will generate moment, carry together with its own forces magnitude and direction. Okay, then it will generate moment, resultant moment there. So these are the things lah. Okay. So these are the application in daily life. Remember, when you move weight or forces from one location to another location, you carry the force. You need to do one more procedure where you need to calculate the moment, the effect of moving the forces to somewhere else, where you get the moment. Okay. Okay, the rest you read. Example 4. This is 2D. replace the force and a couple system shown in figure by an equivalent resultant force and couple moment acting on point O. Yeah. Very high chances you won't see this kind of question in your test one and final exam. You need to choose one point that you think suitable. So this is a tutorial question, it's guided question. So don't expect this kind of question in your test. This is for illustration, just to strengthen your learnings. Okay, so how do you do this kind of question? You are given three forces. You need to transfer all these forces to here. By writing this. Okay, by writing the two equations. So you need to do two things. You need to do two procedure. One is force summation. One is moment summation. Means you group all the force together, get resultant force, and you group the moment together. So my recommendation is to split, when you have a diagram, split all the forces into X and Y direction. Although here do not show you the X and Y in your diagram or in your answer, please show where is your X positive direction, Y positive direction. You just need to draw the axis anywhere on your answer, right? Anywhere near the diagram, then it's fine. So this one split to X and Y axis. What is the X axis value? What is this X axis value? Huh? Huh? Yeah, what? 3 kilonewton multiply cos 30. Okay. Then this one, 3 kilonewton sine 30. Okay. So you break this one, then this one. This one, 5 kilonewton in X direction is what? 5 kilonewton bracket. What divided by what? 3/5. Okay, sorry. Yeah, 3/5. This one should be go down. It should be 4/5. Okay. Then this one only have one direction. You don't need to do anything. Okay. So you split all the force to X and Y axis. So remember when you split, this one gone already. When you split the forces, for example, you split 3 kilonewton, split already into two red arrow. Don't go and count this one already. This one missing. Then this one also, you split to X and Y. Then you sum all the force together. You do all the force like what you learned in your chapter 1 and chapter 2. You sum all the force in X, sum all the force in Y, find the resultant. Square the X, square the Y, find the resultant, find the angle. Okay. So I won't show you the step anymore. I assume you already know. Okay, you find the resultant of X and Y. Then X, this is still in X and Y. Square this one, find the tangent, inverse the tangent, you find the angle for the resultant. Okay. So it just show you that Y is going down. Y is going down. So when you draw the resultant on the diagram, just be careful. Okay. Okay. So when you have X, Y, and what happened when you move force to a new location, this one already explained. So like what you see on the screen here, the two green arrow was added to point O. The green X, FRX is from the calculation. FRY go down because it's negative, in the calculation negative. Don't write negative in your diagram. Huh? There's no negative value in diagram. There's only negative in your calculation. And stay negative there. Okay. Just highlight, always write the direction when you do your calculation, where is positive, where is negative. Or if you're lazy to write this positive, go left positive, go up positive, go to your diagram and draw where is your X positive, Y positive. If you already put the axis in your diagram, then you don't need to write this one. Okay, once you have this one, so recall when you transfer the forces, you'll get a moment. Okay, you get a moment O. Because you are transferring all these forces to here, you get a moment. Okay, FR, you already know how to find. Square this one, square this one, square root. Where is the angle? So find the tangent of Y versus X. Y divided by X. You find the tangent theta here. But how to find MO? MO, you have 1, 2, 3, 4, 5 forces. You are transferring 5 forces, 4 red arrow and 1 black arrow to this location. So this one generate 1 moment, this one generate 1 moment, this one 1 moment, this one 1 moment, this one 1 moment. And you need to fix positive anti-clockwise always by using right hand rules. So for example, 3 sine 30 kilonewton generate what kind of moment to point O? You multiply what? 3 sine 30 kilonewton multiply what distance? Huh? You understand what I'm asking, right? So multiply by what to get moment? 0.2 positive or negative? Huh? Why positive? This one. Why positive? Just now, how by looking at your right hand, what is your positive direction? Yeah. Your general moment direction is anti-clockwise positive already. Then you look at 3 sine 30 kilonewton. This one turn clockwise or anti-clockwise? Anti-clockwise, positive. This one, 3 cos 30 clockwise, so negative. So this one multiply by what distance? This one. This one is perpendicular distance. So 0.1. So 3 cos 30 bracket 0.1, you get negative moment. This one, 5 bracket 3 over 5 kilonewton multiply by what distance? 0.1. Because here, and this one is anti-clockwise positive. Here also 5 bracket 4 over 5. This one clockwise negative value. Multiply by 0.5 meter. Okay. This one rotate like this. So the distance will be 0.5. 0.2 plus 0.3 you get 0.5. Then this one. Don't forget the member here. So this one will give you 4 kilonewton multiplied by 0.2. They give you negative value of moment. So you combine moment 1, moment 2, moment 3, moment 4, moment 5, you get resultant moment. Okay. So this one just show you lah. So you force, you get a angle, resultant 8 point something kilonewton, angle is 49.3, give 3 decimal place or 3 significant figure. So label the answer in the question. Where is your theta? You don't calculate, then you don't label, including this one. So this one, blue color, remember to label. So in your calculation, is resultant FR. You just label where is your FR. You don't need to carry the value. I just want you to show me where does it mean. Okay. Even here, you don't need to write 49.3 here. You only need to write where is the theta. Okay, but you accidentally you write theta over here. I will circle this one. I will circle this one. Even though you get the right value, you won't get marks for theta if you label wrongly. Okay, moment submission, you submit submission all, then you get one value. Okay, now you want get one value negative 2.46 kilonewton meter. You get negative, what does it mean? It is clockwise. It will generate clockwise moment. So you can maintain your answer in negative. Okay, or you can rewrite your answer like this. It's okay, you maintain at here. You don't need to write this one. But you have to understand what is this negative mean. Okay. Yeah. So I just show you lah. I just show you. So this is negative. So it's because earlier I just draw randomly. I just draw it is clockwise direction. So if early you draw anti-clockwise, also can. But if you draw anti-clockwise, your answer must be negative. If you draw like this, that means it's agree. This is a true answer for the moment direction. Okay, now, if your moment you draw anti-clockwise, your answer please remain negative. If your diagram you draw anti-clockwise, your resultant remain negative. If you draw clockwise, then you need to change to positive value. All right, so just test whether you understand or not. So example 15, again, replace all the forces with a couple with the resultant forces and moment to a point O here. Okay, so the SOP always very easy the SOP. First diagram, draw the diagram. 2, look at forces and moment. Then you calculate resultant for force and moment. Then check lah. Number 4 is just check your diagram whether correct or not. Okay, so you draw a diagram, you transfer the whole object to a new slide of paper or new space. Copy all the dimension. Copy the old location. Then the next one, you look at the forces. As long as forces with the angle, split them into X and Y direction. And that is the first step. When you see forces, first step, you split them into X, Y direction first. After you split them X and Y, then you do the resultant forces, resultant steps, like what you learned in chapter 2. You group all the force in X, you group all the force in Y, then you find the resultant. Okay, where is the the resultant in X, resultant in Y. Then you find the final resultant where you square the X value, square the Y value, square root. Then you need to find the angle also. How to find angle? You use tangent theta equal to Y divided by X. All right. So it depends on your diagram. So then you transfer all the force to here. When you transfer all the force to here, remember you are creating moment. When you move forces around, they create a moment to that particular point. Yeah, on this diagram, there's no additional moment, so so you don't have worry of additional moment. You just need to transfer all the forces into moment. Okay, this generate moment. This have two moment. Okay, this got one moment. This got two moment. Then this one also got one moment. Or you can straight away convert this one as one moment because this is a couple. 200 to 200. You can convert this one as one moment. Then move this moment to here. Or you can remain as one forces here. You can move to here, same. So it depends on how you see it. Okay, so I'll show you the steps. Again, you have two main component steps. You do forces and then you look at the moment. Okay, this one is force summation is what you learned in chapter 2. So you do all the forces. For example, this one 500 to x and y. Okay, what is the x component for 500? 500 multiply what divided by what? 3 over 5. Okay. So you resolve into xy. So when you resolve already, then this 500 gone already. Don't calculate in your. Okay, then you do all the force in x, do the force in y. So x, you only have 3 forces here. 500 bracket 3 over 5 minus 200 positive 200. Okay. So basically you arrive at 300 because these two cancel each other. Y, you only have 1, 2. So you have minus 350 kilonewton. This one you assume go up positive. Go right positive for x and y. But you get negative. Remember, when you transfer value negative to diagram, remember to show the correct one. Negative means go down. Okay, so transfer these two value x, y resultant to O. So draw positive 300, negative pointing down 350. From here, find the resultant. Square 300, square 350, square root. Find the angle, tangent theta, y divided by x. Okay. So I show you lah. This one should be shown in your diagram. So find the theta. So this one just remind you when you transfer forces, there is consequences. Okay. If you move a force along the axis, nothing will happen to the force. But if you move forces that is perpendicular to the axis, it will generate moment plus carry forward the forces. Okay. So again, in this case, I still very stubborn. I assume my final answer will be clockwise. I just draw like this. Okay. So you can draw anti-clockwise if you want, right? But this one, later I need to check my answer. Okay. So I guess no question for the forces already. Right? So I move on to just remember to label your diagram. Just remember to label diagram. Then you move to moment summation. So all the red arrows, all these, so 1 moment, 2 moment, 3 moment. And this one you can convert in 1 moment if you want, or you can break into small moment. Okay, so this one, you combine all the forces. So this one, negative, because we assume anti-clockwise positive. So this one, move here. So you multiply by this distance. 200 here. So this one I just coupled as 1. You can break this one into 2. 200 multiplied by 0.5 if you want. 200 multiplied by 0.5, you still get 2 moment. Combined, you still get this value. This one, 4/5. This one is rotate anti-clockwise positive. This one negative. You combine, you get negative value. And this one in your calculation, anti-clockwise is positive, and you get negative. It means what I project in my diagram is correct. Okay. Any question for example 15? Yeah. So means this is what I assume correct lah. Okay, structure number 6 is more on the civil structure. So you see there's a lots of forces there. All right, this is a 3-dimensional. Replace the system equivalent force and couple moment of base at point O here. So you're given X, Y, Z direction. All right. Now, before you solve, you should already, in your mind, you should know what to do already. You need to sum all the force in one group and sum all the moment created by the forces. There's one moment here. There's one extra moment here in this direction. And in the question, you see R means it expect you to use vector analysis already. You see the R, you see 3-dimensional, most of the time you need vector analysis. Vector analysis means you need to use R cross F. Just now, just now is a scalar method, F multiplied by D. If you see 3D, most of the time you need to solve in vector analysis. Vector analysis, you need to find the R, find the U, find the force. You need these three. Okay. How you do? So you have 3 steps in vector analysis. You need to convert all the forces, all the moment in IJK. You need to decode everything in IJK form. Okay. So for F1, go down, negative, bracket, negative, 800 kilonewton. Not kilonewton, Newton in K direction. Go down. Z is K. So decode F1 into IJK form. F1 go down, minus K. F2, what is F2? How to do F2? You F vector equal to magnitude of F multiplied by the direction of the force. This one you calculate by R divided by R. So F2, I just put a value of positive, magnitude positive. I need to find whether it's positive, negative in the 3-dimensional IJK. So U, C to B, write carefully your notation. B to C and C to B is different direction. So what is RCB? What is RCB? RCB equal what I plus what J plus what K. RCB, how many? How many steps? 2x. Positive, negative? Negative 0.15. y. Okay, y is 0.1. Z 0. So this is a vector of R. Find the magnitude. Square this one, square this one, square this one, square root. You find the magnitude of R, PV, equal to something. Divide each one of these, you get the UCB. Okay, this one is already covered in chapter 1. Chapter 1 or chapter 2. Okay. Yeah, of course, you can write plus 0K here lah, if you want. So at the end, you get F2, you get one answer. We're still now decoding all the forces. Okay. What about moment? Moment also same, have magnitude and direction. Also same. So moment of this one, again, 500. And the UM, U, this direction. Right? So first one, you have 500. It goes back to Y direction because this one is in Y direction. So no I is go along this plane. So this Y direction. So your 0I do not move in either X direction. So 0I. Then J is this distance. Here to here. So here to here, you need to look at this triangular. Okay. So it's 4/5. Okay, 4/5. If you don't know how to do this one, go to your mathematics textbook. Go and see how to do this one. Okay, and it's negative because it's go against the y-axis, positive direction going here, but this one pointing at the back of the y, so negative. Okay, careless mistakes always here. You give positive value. What else? What is that? What is that value? 500 bracket what? 3/5 what? Okay. Okay. So this is how you do it for a moment. Okay, once you have that one, you do all the force together. You have two forces. Combine IJK together. This one don't have I, so pull the I together. This one don't have J, pull the J value. This one, pull the K value. You get this answer. Minus something, IJK. Moment, you just, moment you need to do a bit. Okay, now moment you have resultant done by these forces. These resultant forces will generate moment. And you carry this moment together. Later, you need to combine this M, the moment created by FR. Okay. Okay, so for vector analysis, you don't need arrow. I just put here. For vector analysis, IJK, no need, because you already tell me where is IJK already. Don't need this one. So vector analysis is R cross F. R cross F. So RC multiplied by F1 plus RB multiplied by F2 plus M. Okay, right, right, this one. R cross F, you have two F there. So RC cross F, RB cross F2 plus M. What is RC? What is RC in IJK? 1K. 0I, 0J, 1K. Positive, So, what is RB? What is RB? 5 RB. minus 0.15 I, go back, 1.5. J, what is J? Here, right, here, K. K, 1, 1 K. So you have a IJK already, you have a R already, you just do the cross product. Okay, multiply by the products. So 1K for the RC is quite direct because you only have K and K. All right. So again, you have two procedure. One is dot, one is cross. Dot I, you get 1. But cross one, remember you have a circle to remember, IJK. Anti-clockwise positive, clockwise negative. This one, I, cross I, you get 0. Okay, so K cross K, 0. And this one, you do lah calculation. This one is R, this one is K. You do your calculation. M, you copy. At the end, you arrive at one answer. Okay. But this is how you do it. Okay. Then next question is how you draw on the diagram. You know how to calculate, but how to draw? Where is FR? Where is FR? Where should you put FR? At point O lah. Question already asked you to put here already, ma. Okay. So FR, draw here, then you need to tell the IJK, right? So of course in test you don't need to really show me the 249.6, you don't need to do here, but as long as you need to show me where is the direction, where is the direction of negative X, positive Y, and negative Z. Means positive region, negative region, and so on. Okay. MRO also same. MRO also same. How to draw this blue arrow? How you know is this anti-clockwise direction? Find the magnitude lah. Square, 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 square root. Right. So it's anti-clockwise direction. So right hand rule. Okay. Okay, with this we conclude 3. The rest is just application, right? The rest is just application. So this one I go very fast. So let's say you look at this question. You have four forces. You just sum them to become a systems. Okay, this one you should be able to do already. Yeah. Means you can transfer the force with an axial line. You just draw a simple line from F to the center to the focus point that you want. All right. Or you draw a line and then join intersection point, transfer all the force to that. Right, then you get resultant. Why no moment? Why no moment here? Huh? No perpendicular distance because you are actually moving the force along the line. You can move the force along the line. Okay. Another one called planar. Core planar means you cannot draw an intersection point. for all the force. Then there will be a resultant and moment for one interest point there. This is what we've seen for the past 2 example or 3 examples just now. Okay. And you can convert this diagram. You can convert this diagram in the middle to the third diagram, where you can cancel out the M by moving your resultant. This one clockwise, right? This one anti-clockwise. Anti-clockwise. So how you cancel anti-clockwise? Not cancel lah, but how you equal this moment with this force? You move this force with the one distance. Okay, you move this FR to a certain distance, you're creating moment. It will sum out this MR. You're equal to this one. Okay. This middle one and the last one will be the scale factor in. You should able to see this one is in the question. You should able to solve this one like what you see in the previous 2 question or 3 question. This one is more in application. This is what you need to know when you go to work. Because in work you don't see moment one. You need to balance the moment by shifting the forces that you add. Like maybe you hook a wire here just to balance the whole thing. Okay. Okay, the rest you read. So same with this diagram. So the same traffic light just now, you can equal the 2 forces and balance all the moment by shifting the weight to a certain location without creating a moment at this arm. You can cleverly design a weight where it is shifted to a certain location, it cancel out all the moment. Not cancel, but it shifted, balance all the moment. So this one won't bend over. Okay. Okay, so this one is what you see in the question. You have a 3 forces and there's an interest point O. When you transfer these 3 forces, you get resultant force and a moment at this point by using the procedure that we have discussed. Right? So you arrive at the middle diagram. Then to eliminate the moment, you can shift your FR to a certain location. How you know which axis to go to cancel the moment? By using right hand rules. You know this moment R here, right? It is what? It is anti-clockwise like here. So you know that you need something to cancel this one. So this one, you can either move to inside or move out, right? So this one is anti-clockwise. So how to cancel the thing? How to add this moment into the diagram? How to transfer this one in the force term? How to transfer this MO anti-clockwise moment? You can just shift your FR along the B axis. Then you will create an anti-clockwise moment. Right? You are not changing the forces, but you are doing an equivalent of this moment. Okay, so this one, how you change from the middle diagram to the right hand side diagram? You want to eliminate this MR. This MR is anti-clockwise. So how to generate anti-clockwise? For this moment, you move your FR along the B axis. It will generate anti-clockwise moment. Don't move the wrong direction. If you move inside negative B direction, you are actually creating a new moment for the diagram. So just need to be careful where you move. And take note when you do three-dimensional movement, move in 90 degree. Move in 90-degree axis to eliminate the moment. Okay. So let's say you have a moment given. You can split your moment in two axes. One is parallel, one is perpendicular by this symbol, perpendicular. You have two axes. So you can eliminate this moment by moving your force. You can eliminate this one in your diagram by moving the FR along the axis of B. So this one is anti-clockwise. How you move FR anti-clockwise? You cannot move inside the B. Inside B, you are generating clockwise direction already. So you need to shift your FR along B so that it will generate anti-clockwise moment. So this perpendicular will equal to FR multiplied by D. It will cancel the M perpendicular. Okay. You can also eliminate parallel moment by how? By moving this moment parallel to the R. You can shift the one that's parallel to the new location without affecting anything. Moment can move in parallel one because your thumb is always pointing out. Your finger always curve. So conclusion here is that when you move perpendicular moment, you can cancel. You can cancel perpendicular moment component by shifting the forces, and nothing will happen to the magnitude and direction of the parallel moment. You can shift anywhere as long as it's pointing up. The axis pointing up. So you can combine the system on left, summarize the one and on the right. Yeah. Okay. Okay, I think we stop here. Yeah, stop here. There's a replacement class today. 4 to 5. Replacement class. You have class? No class. Anyone have class? Anyone have class? No. I just get if we do. Yep, not here. Okay, now we can do class now if you want. Can. Or you want to do afternoon? Okay, so we continue lah. Okay. Okay, I think we go for another half an hour. Then I think we can conclude chapter 3. Can No, nobody have class, Okay. So we continue a bit more. So this exercise number 17. The question asks you to replace forces and couple moment system acting on beam. And it asks you to focus on point O. Mean you shift everything to point O and equal to an equivalent system. When you see 2D, you can use scalar method, means F multiplied by D. If you see 3D, you need to use vector analysis, IJK. All right. So first, you copy the diagram, the shape, the dimension you copy, and this one even give you the X positive, Y positive direction. Okay, once you copy the diagram, you look at the forces. you split all the forces with angle into XY direction. Okay, once you do, you're done with the diagram with the forces and the moment. You see there's additional external moment there. Once you have the diagram ready, you need to do two main things. With this, you need to handle the forces equation and you need to handle the moment equation. There are two main steps there. So for the forces, you do find the resultant of the forces in X, in Y, then find the final resultant with the angle, transfer to O. Okay, transfer to O. Then after that, you do moment. Carry the moment of this blue color arrow, and each one of these forces will generate moment. 4 kilonewton will create one moment. 8 kilonewton will create two moments, one in X direction, one in Y direction. Yeah. So you will see your answer have 4 moment answer. 4 kilonewton create one, 15 kilonewton meter, and 8 kilonewton in Y direction create one moment. 8 kilonewton in X direction create one moment. We have 4 moments. Then transfer the answer to O. Okay, you can draw anti-clockwise if you want, but you need to check carefully your answer. If you draw anti-clockwise, your answer moment positive means remain as that direction. If you do anti-clockwise and you get negative, you need to go back to your diagram and change it to the correct direction. Okay, your diagram always showing the correct direction. Okay, your analysis can be negative, no issue. Can be no issue. And no negative in diagram. That is what I can remind you. So I just show you very quickly how we done it. You split the forces in two directions, combine them into resultant, find the magnitude, find the direction. Standard already, this one's standard already. I mean the step standard lah. Step standard already. You do this step, after that you do this one, you do this one. Standard already. Okay. So here we have the FR, and we have the theta, right? We have Fy, but we don't know the distance. We don't know the distance of FR. Now we don't know the distance of the FR. Because now you have an additional moment, so you don't know. So you just put a D there. Okay, you define the D. So we need to, this question asks you, find where is the line of action of intersect of the beam. Measure from the point. He asks you measure from the point. It means you are not on the point. I flip back the previous question, you see what is the difference from the question. At point O. At point O means you transfer everything to that. If the question changed to this measured from O, he asks you to find intersect, means it's not on point O. It is somewhere along the line. So read carefully lah. So you only can find the resultant, the angle, but you don't know where. Where is this force? So you draw on the diagram with the green color, 480, 240, 2.4, and need to help me check. This one might, some decimal place might be missing. I think it's 4.8. But anyway, help me check. I think got typo error here. Okay, so what else? Okay, so I just skip the steps. So you just now you place your FR over here, and you have your FY. I think typo error just now. My value in my slide is wrong. It should be 4.8. Right. Then there's a distance here. So you need to summarize the moment. The one on the left equal to the one on the right. This is a direct comparison between the two diagrams. This is the resultant diagram. This is the component diagram. This is a resultant diagram on the left. This is the component diagram, means before you break them. So you got component 4 kilonewton moment. You have 6.4 kilonewton Y, 4.8 kilonewton X. To find the moment, to find the location of D, you use an approach of the right-hand side diagram will equal to the right-hand side diagram, left equal to right. So you write equation, all the moment resultant equal to all the component moment. This is the new thing for the second half of the lecture. And because you are comparing, you need a direction. So give direction anti-clockwise positive for the both diagram. Okay, so what should you write on the left-hand side? By measuring from O, what is the moment you get? Do FRX generate moment? Do this generate moment? No, no distance. FD, no distance. Only FRY 2.4 kilonewton generate moment anti-clockwise with the D 2.4 knd put here left hand side. Then this one got right lah. Right hand side you copy the moment 4 kilonewton multiply 1.5 negative value. Then this one 4.8 positive value. Sorry, negative value. 6.4 multiply positive. Okay. Any question on the steps? Any question? Can So here only have one unknown. So it's just solving linear equation. Balance the equation, you get the D. Yeah? So read carefully the question, either at point or from where. There are two kind of question. But for example, this one, find a line of action that intersect measure from point O. You need to call out this equation. You need to compare resultant diagram and the component diagram. You need to draw two diagrams. Then you write this equation, then put your answer and find. Okay. Example 6. Again, it asks you to find equivalent or resultant forces and moment. Specify where the resultant line of action intersect the column AB and DC. And this one is more on the application. Okay, so you're given all the things there. You don't know where is the line, where is the location for the equivalent. So you copy the diagram first, and then split the forces into X and Y direction. You are given X direction positive to the right, going up positive. Same. So split all the forces into X and Y. Then find the resultant. Okay, split all the forces in X and Y. Find the resultant. Find the angle. But you don't know where is the resultant. You don't know where to put the resultant, never mind. Later you compare resultant diagram and the component diagram. Okay, so I show you. There are two steps also, like just now, force and moment. Okay, so this is just same as previously. So you just go and do the same procedure. You will get resultant for x equal to one value, y equal to one value, both negative. So when you get negative, remember when you draw in your diagram, flip to the correct direction. So magnitude is a square, x square and y square root. You get one answer. Then you need to find theta. Again, standard procedure, this one, standard procedure. The value just change in the question only. Once you find that one, you go to the moment. Okay, so this one, we assume, you can assume at anywhere. This one, we do point A. Okay, you can assume in anywhere, but here I just assume at base A. So when I assume my moment at point A, I will be seeing this diagram. I'll be seeing this diagram. Okay, so where is this one? So you are having Rx, Ry, and resultant is 1.7. Theta is 40.2. This, okay, it can be here, it can be here. It can be along this member or it can along this member. Okay, so my resultant is along this axis, along this direction. Okay, so I label. It can be here, but with the distance of x. If I look at member BC from point O, from point A. So this one you need to think a little bit where you want to put your thing. Okay, you compare left, actually compare this diagram and this diagram. So you find resultant at point A equal to the component from point A. Okay, resultant from point A compared to the component diagram of A from A. Okay, so we assume the line of action of FR intersect AB at the distance of Y from A. That is Y. So line of sight intersect AB with the distance of Y. This one. Okay, so this line can be anywhere as long as it's going down 40 point something degree. It's going this direction. It can be here, it can be here, it can be here, anywhere. Okay, it can be here, it can be here, it can be anywhere. As long as it's going this direction, because it's vector. So you don't know. So if you adjust this one, we put like this. So you have x direction and y direction. So from A to here got y direction. You do the equation, you do this calculation towards A. So how do you do side by side if you from A to Y? So left hand side, this one, what you do? If you're A, do you have 1.1? Do it create moment? No. 1.1 do not create moment if you're at A, but 1.3 kilonewton will generate moment anti-clockwise, positive. Multiply by Y, you get left hand side. This one, you look at here. Point A. This one, clockwise. anti-clockwise. One moment. This one clockwise. Second moment. This one break into two. Okay, this one break into two. So one anti-clockwise, one clockwise, one anti-clockwise. Okay, so this one you got 1, 2, 3, 4, four equation, four component at the right hand side here. Solve the equation, you manage to find y. Okay, so find the direction of x also by the same method. By the same method, you put in this x direction. So x direction, 1.3 do not generate moment, right? So from A. Okay. Okay, from A, if you put here, you are having this resultant, you have 1.1 multiplied by the x plus 1.3 multiplied by the length of 4. If you put here, you have two moments. One is anti-clockwise, one is clockwise. Sorry, one clockwise, one anti-clockwise on the left-hand side equation. Then you move to the component diagram here. Here, you still seeing four moments. Balance the equation or solve the equation, you get x. It depends on where you want to see here or want to see from this member or this member. Same. Yes. Any question? Do you need me to write the detail for you? Yes. Means you don't understand what I say just now. Left hand side. This one. Basically, you're playing around with this. All the moment in resultant diagram equal to the component diagram. This is component, means small forces will create moment. This one is only have one resultant diagram. Okay, so we have two member there. Member A, B, C. And from just now, from the calculation, you know that you have two direction of forces, Frx and Fry. This one you have value, this one you have value. And you know the resultant with a certain angle, either here or there. I think it's here. Right? So this one already fine, all this value. But we don't know the location. We can put this resultant here, 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 doesn't matter. Because this is vector. So we just assume any location on the diagram. So let's say this is the location of our resultant. This is our resultant for forces. And you can see this is the member. We have two member, one AB, one AC. And we focus on A. So when you focus on A, this is line of action. You will have a distance of Y. You have a distance of X. Yeah. So when you have this line of action of result X and Y direction, because you need to tell your technician, hey, go and hang something in that direction. Okay, so we need to solve Y and X. So how you find, let's say we find for Y first. So find for Y, see the diagram has two member, A, B, and C. So this is point A. So when you move your resultant to this location, you want to find Y, your vector is like that. And you know that your R can split into X direction, Rx, and Ry, Fry. Sorry, Frx and Fry. Right? Uh, so you know this one already. So this one is resultant equal to in this diagram, you have 7 kilonewton, you have 0.3 kilonewton, you have two components here because you split 1 kilonewton into this direction. So you have two components of 1 kilonewton in X direction, 1 kilonewton in Y direction. So we have four forces here. Okay. So if you want to find Y from point A, both from point A. So how you find moment in here? So this one do not generate moment. This one generate moment. And you say anti-clockwise positive. So this one, you take okay, positive Fry, which is this direction, 1.13 kilonewton, multiplied by the Y distance. Nothing more, ma. Here on the left-hand side, we clear already. Equal to 4 moment here. 7, 7, 2 plus negative 7, 2, 0.3, sorry, positive, anti-clockwise. Okay, anti-clockwise. Then negative 0.31. Then got two component there. You calculate lah. So this one got 1 kilonewton in X direction. X direction will be anti-clockwise, negative, positive. 3. Then you got negative 1 kilonewton Y direction. Sorry. The X one should be 4. Y one should be 3. Okay? Yeah. Which one? This one. X. X. X is that direction, right? X. Oh, time 4. Oh, negative. Hey. F then. Y negative also. Okay, so you get this equation. You are solving for Y. Cannot, cannot. This one. You okay now? This one. Can I? You solve this one, you get Y. Then you solve for Y, then you answer for X. So same. This is your X. Your resultant is over here now. So you have your Y, you have your X. So equal to this diagram. A, B, C also have 4. So you anti-clockwise positive moment. So here you have anti-clockwise moment. You have this one. You have resultant Y. to A, to A. Well, we have x plus minus, minus yx minus 4 minus rx 4 equal, then this one same, this one copy. Okay, this side is the same. Okay, so here if you want to do 7 from A, same, 2 minus 0.31 minus 1 kilonewton in x. This one will be here. Yeah, from A. So that's why you have. Our x will be here. We are referring to A. Here 1.3 multiplied by this distance. Anti-clockwise. Positive. Then y clockwise, negative. Understand? Ah, ah. This one? This one. This one. This one. No lah. You have to find the x direction, y direction by using this triangular. You split this one in this direction and this direction. You need to split this one in this direction and this direction. This one? This one is the magnitude. This one is magnitude. So this one is okay. This one is 1 kilonewton. What is this component? 1.1 K. This one is 1 kilonewton bracket 3/5. So this one is here. This one is this one. Multiply 4. This one, here. Okay. Any question? Yeah. So yeah. So example 19, you go home and see. This one is balance the point and also need to locate the point on the slab. This one, if you're taking civil engineering, this one, you will see this kind of question in your other module. Okay, go and see this one, your homework. Go and see. Still the same, you have force and moment submission. And you need to compare side by side again, resultant diagram and component diagram. Balance the two, find the X and Y. You don't need to draw this one, but at least you know what you're doing now. Because this one already in the question. So important is the resultant diagram. Okay, say example 20 also same. This one, example 20 is on the three-dimensional, so expect to use vector analysis. So vector analysis also same, you just use R cross F. Then you compare resultant diagram and so I just show you the general steps. The rest you see, got question come to me. So you sum all the force together in IJK. Okay, you sum all the force in IJK. You get one final answer for resultant. Okay, then you draw on the diagram. Where is the location of the force? It's over here. Okay. So you are referring to this one. You're referring to this one. So you substitute all the value there. How to, okay. This one also we assume RP as in this quadrant. We assume it's in this quadrant. Okay, if you put in the wrong quadrant, also never mind, you get negative value. Good negative value, then you flip back the direction. Redraw, you need to redraw. Yeah, you need to always show the correct diagram. If you draw, you found out that the answer is wrong, the answer you get negative, but your diagram, you need to flip, draw a new diagram. Your diagram always need to show the correct direction. Okay, this one you go and see your homework. This one is more reduction of the simple distributed loading. This one, something like this. Have you learned this one? No. Okay. So just now is all the while we are seeing one arrow. One arrow called concentrated load. Means everything focused on one point. However, in the real life, they're exposed to air, exposed to pressure. When you do simulation, we are using pressure, Newton over meter square pressure. Right? So on the road sign, on the silo, and the one that we ready for the concrete things. So we will use this diagram with a loss of arrow with a different distribution. You'll see a graph with this distribution. This is called distributed load. Distributed load, don't worry, they already have a table to help you to find the location. There's a formula given how to find the X bar and so on. You don't need to memorize. You only need to know there's a table for you to refer. The table will be given at the back of the question. It's just a table for you to refer. Oh, to find location, okay, find this shape, then you refer. Okay, to find the when you're given this distributed load, you'll be given P equal to P bracket X, means in the distribution of X function. Okay, for example, you'll be seeing W equal to 3X kilonewton meter. Okay, per meter square. So there is an X value there. X means the length. Okay, so what you do, you just multiply the length and then refer to table to calculate the resultant. Okay, so to find the W, to find the value of the weight or load, you just multiply the equation with the length. Now, for example, in 2D, you're seeing this distributed load. So you go to the equation there. You will see W equal to how many X kilonewton over meter square. So change this one by multiplying the X that you have, right, to become a force, to become a concentrated force. So you convert the one on the right to become the one on the left. So when you combine all these force, become one concentrated force, there is a location for the force. This location, don't worry, this location refer to table. Okay. So in summary, every time you see this one, multiply the length, then go and see table. What is this shape? What is this shape? It can be pyramid, it can be triangular. Don't worry, go and see the table. And important is to find this distance. Why? Because this distance will give you moment. This one will give you moment. Then you continue with the step that you learned just now. Okay. Okay. This is unit integration sometimes. Unit integration. So integration, you just integrate the length. If you are weak in integration, go and do integration exercise. If you don't know what is integration, go and learn integration. Okay. Then moment also same. Moment, you just take the forces, the integration of the forces multiplied by the x. You compare left hand side equal to right hand side. Same, you still need to compare side by side two diagram. So the one on the left is resultant, the one on the right is the component diagram. Okay. So you can either memorize this one or you draw two diagram and you do the calculation. Okay. Some of you manage to remember, then you remember. If not, then you do draw two diagram, solve the moment equation. Actually, the same concept lah. It's just this one on the right hand side got the integration steps. I think. Okay, so you can either remember this one. Okay, it's important that to find the centroid. There's one specific chapter for to find centroid. At the moment, I don't want to go that direction yet. At the moment, I just introduce you what is distributed load. Okay. This one, go home and see the things. Okay, so this one, if you remember in X linear form, is the location of the X bar will equal to integration of your area under the graph equal to small component of X dA. Okay, this one in three-dimensional, you just walk through the things. It's the same thing. Now, for example, this one, example 21, then I think we call it a thing. So determine the magnitude of this one, the resultant. So you have this shape with W 60 x square Newton meter with the length of 2 meter and area of individual, this one, how to find area is W multiplied by small dx. So you need to integrate from here to here. You find the magnitude and location. Magnitude, you integrate this shape. This one is an application of magnitude. So resultant, you know that this one pressing down, so go down positive, equal to the sum of forces in the component. So you integrate area under the graph, because this is distributed load. You need to find this distributed load multiplied by the length with this area under the graph. So you need to integrate the area under the graph. Also means you take W equation, integrate with x from 0 to 2, x1 to x2, W dx. Okay. So again, how to find area under the is W and substitute the equation W equal to 60x squared. You're able to know, right? To do integration, right? If you don't want to confuse yourself, pull the 60 out. This one, new number, x cubed divided by 3. So you get 20x cubed. 2, 0 in the answer. You get 160, 0. 160 Newton. Resultant go down. Okay, that's right. So this is integration steps. Important for this module is here. You know that find the resultant force for the distributed load is multiply the length with the formula. Okay, now is a location. Location of x, I straight away use the equation of this one. You can either remember this one or remember this one, doesn't matter. So x bar multiplied by the w dx, you get equal to xw x dx. So basically just application of integration. You substitute the value here. So integrate from where to where, dx, right? So dx is from 0 to 2, so 0 to 2. X you copy because you want to find the x. W is given. W bracket x means the function of W, the equation for W. This mean equation of W given in the question. Copy this value, put here. Divide. This one also same. The length is from 0 to 2. Wx also function. Copy 60x squared here. And dx, do the calculation. So here you multiply inside this one 60x cubed. Then you do the integration like what you see on the screen here. Save. So I assume you already know. Do integration, get x power 4 divided by 4. I just now 160. So once you find that one, oops. So you have this value. X equal to this value. Value 160, you get the x bar 1.5 meter. So for the final answer, once you find the two resultant, draw the resultant. Remember to draw the diagram again with where is the FR and FX. Copy the outer shape of the distributed load. Like for this one, the almost triangle. Okay. Copy the outer shape of the distributed load. Then put in the diagram where is your X bar in your answer 1.5. If you scared that your answer is wrong, you just don't put 1.5. You put X bar. If you scared lah, if you scared, you're not confident with your answer, then don't put 1.5. Then this line must go with the X bar. Then label C here. Label C here. C is your centroid. Is where all the force focus on is at C. So put in C there. Then label FR. Okay. Nothing complex. Huh? So same, this one is in 3D. What you need to do is convert into 2D plane, then convert the boundary condition. This one is X at 9 meter. So this is a right triangular distributed load. Here is 0. So you need to multiply this load, this pressure, 800 X Pascal. You need to calculate what is the boundary value for this one. So you take 800 multiplied by 9. You get 1440 Newton. So here, 800 X multiplied by 0.2. Oh, okay. So this one, you in 3D, you need to multiply with the width, the width here. Okay. So you multiply by the width. So this one is in Pascal. What is Pascal? Pascal is Newton over meter square. You multiply by the thickness, the width. You reduce the equation into Newton over meter form. So you become 160x Newton over meter. Take the W, put back the steps that you learned just now. Okay. So this one, 160 multiplied by 9, you get 144 Newton. For 3D, remember to multiply the width here. For 3D, for 3D, reduce the equation from Pascal to Newton meter. Okay, then draw the XY diagram. Convert 3D into 2D diagram. These steps, extra step when you see 3D, convert this one to here. Then this one you see triangular, you draw triangular. Copy the equation that you just converted. 160 Newton. Here is 144 Newton. Then you don't know the X, you just put in the X. You know the length, 9 meter. The next step is the same as example 21. The following side is the same. Okay. The same steps, It's the same steps like just now. Then you find the resultant and find the X bar by substituting this inside this equation. X you don't know, you remain. This one you copy from the reduced equation. This one also you copy from the reduced equation. Do the integration. Do the integrations. Important is the limit here. Some of you don't understand why 0 and 9. This is the X, the length of the bridge or length of the bar. Your integration is not in area, but in X. You substitute, you get X equal to 3. Because this is not a parabolic triangular, it's a standard triangular. So what does it tell you? You see 9 and 6. What does it tell you? The location of a triangular distributed load always where? You see the relationship? X bar here is 6. Total length is 9. So in triangular, the location of the centroid or the pressure point, where? 1/4, sorry, 1/3 from base, from the big base, not from the tip. If you calculate from tip, it will be 2/3 from the tip. The location of that one. If you have a standard triangular. Remember that. Okay, so if you see standard triangular, we assume we already know where is the location of the X bar. Okay. So this one is just to introduce you. If you have you only use this equation when you see parabolic shape. If you see standard triangular, straight away remember it's 1/3 from the base or 2/3 from the tip. You can skip this step if you see standard triangular. What about a stupid question? What about a square? What do you think? If you have a square distributed load center lah. Okay. Okay, the rest again, remember to draw the diagram. This one, go home and see. There's a table. This one inside the canvas, go and download. Go and see. So if you see different shape, don't go and compare lah. For example, triangular, go and see where is the distance from here. There's a formula here. Although very small but there's it already tell you where's the location from here and so on. Okay, so these are the things. So for example, this one a bit small. Okay, and large. So you will see is from the base 1/4 the centroid. This one from table. So go and see example 23. Okay, with this we conclude chapter 3.